verbally to Olivier. So I want to welcome Olivier Blais to our Create seminar series, if you will. And I'm very excited to have Olivier today. Olivier is a co-founder of MoovAI, and he's also an expert in data science, in machine learning and AI. And I think he's also dabbled quite a bit in software engineering as well. So it's great to have him here and to have the practitioner's perspective as well. I'm very appreciative of Olivier coming talking to us, and I look forward to a very lively discussion at the end of his talk. So without further ado, Olivier, the floor is yours.
Great, thank you, Matt. This is really nice, and thank you everybody for joining. So I'll share my screen. Give me just 1 second.
Yep.
Excellent. So you can see my screen right now?
Yep.
Excellent, great. So today, what we'll do, we'll talk about delivering high quality ML models or systems. So here, So maybe add a little bit to it. So I think it was already a good introduction, and thank you very much again. Maybe something else. So I've been I started my career in business intelligence, and then I pivoted into machine learning data science about 8-9 years ago. So I delivered a lot of different solutions. So I failed quite often as well, and this is where you start. You learn from your mistakes. This is why I decided to focus early on into quality of machine learning. I think this is important because it's so often we think about the solution, we think about the algorithms, we think about the data, but we never challenge ourselves, and we rarely validate that what we deliver is really creating value for customers. So this is why I decided to focus on quality. And currently I'm a project editor of an ISO standard on quality evaluation guidelines for AI systems. So I'll try to stay a little bit further from talking about the standard. It can be quite long because it's like a long list of processes and so like that. But we'll talk about quality. So what does it mean to deliver good quality, and what different type of tools are there? What different type of process do we need to think about when we deliver AI? And here, and I think I said it all. Why do we want to do this? It's because, and here, I was very shocked when I saw this. So according to Gartner, in 2022, 85% of the AI project will yield erroneous results. So this is a real challenge. At the end of the day, if we're not able to deliver results that are useful, so it will be very hard to get adoption. And our goal with this technology, the technology, even though we see out there in research, in academic papers, in research, we see some success stories, and this is a useful technology. But if we're not able to generate adoption from companies, it's going to be very hard to stay to keep evolving this technology, because it might not be as useful as we think it is. So this is why here I started to spend time and trying to understand, so what can we do to revert back to delivering quality. One reason why I think we're not delivering quality is because it's the Far West. We don't talk enough about quality. We don't even have rigorous process and tools. And if we do the comparison between software development and AI, I think this is the purpose of SE4AI, and also this is AI is software development, and we'll come back to it in a second. But in software development, it was the Far West at but it was like 10 to 15 years ago. And what they did, they created a lot of different tooling and a lot of different approach, a lot of different process that they need to follow in order to deliver a software solution. So why don't we do that in AI? It's just because it's lack of maturity. It's also because a lot of the AI initiative are undertaken by mathematicians, by scientists who don't necessarily have the software engineering background. So I really like the initiative that you're undertaking of, trying to bridge the gap between software engineering and AI. I think it's going to help getting away from the Far West that we're currently in. So how do you deliver a project of good quality? It's not rocket science. So first you need to understand what's quality. Like, I think it's easy to say, oh, I'm delivering quality, but delivering quality is not necessarily to have the perfect model. It's much more complex to understand, but it's logical. Like you won't fall, like you won't lose your mind, like, oh, this is unexpected, this is totally expected. Just that we need to think about what's quality, and then we need to be able to measure. What gets measured gets done. And this is why we need to measure a lot what we're delivering to validate that we're delivering something that's useful for the business, that's not prone to errors. That will be helpful in a short, medium, and long term. And then it's we need to then develop some process, so some quality evaluation process and feedback loop. Okay, I'll explain more in detail. So today I'll spend a little bit of time on these different type of process and measurements that we can think of. Okay, so here just to go back, the different, like when we're thinking about AI, at the end of the day, it's a computer system. Okay. The computer system that performs tasks, and then the core is machine learning. So yes, we will have a machine learning model, but it's going to be a lot more. It's going to be a lot more. So here, a system looks like this. So we have a lot of different components that need to be delivered. From our experience at MoovAI and also from other experience, there's about 20% of the effort that is model related. Okay, the rest, it's all around the system. So making sure we have the right input, we have the right infrastructures in place, the right tools. We configure, like everything is well configured. We have the right quality assurance processes and the right monitoring tools. So this is important, and usually this is not something that people talk about, especially when we learn about machine learning. So we learn it from errors. It's not very well democratized for now, but we need to think about an AI solution, an AI system this way. Okay, so we'll have the model, and usually we tend to spend a lot of time on the model, but there's a lot more. If we look at it from a quality standpoint, so we have the AI system quality, and we'll have different characteristics that expresses what quality means. So quality is first the functionalities that you develop, because it's a software system. So the model essentially is a functionality. So if you want to predict the demand, the functionality is, okay, I generate a prediction of the demand. So having the quantity of product that a company will sell in the future. So that's a requirement. And then being able to meet this functionality well is important. Duh. Okay, this is something that usually we'll think about, but then the system is performance. So are you able to take the load of requests? Are you able to meet the speed requirements, the resource? So here, I'll give you an example. If you build a recommender engine, this is fun. Building a recommender engine, this is fun. This is super interesting. But there's a difference between being able to generate recommendation and being able to generate recommendation for potentially 10,000 people in parallel who need to have recommendation in less than a second because it needs to appear on a web page. So if you don't, you could have the best recommendation there are. If you're not able to meet these speed and load requirements, the system is not very useful. So we need to think about this as well. It's going to change the requirement. It's probably going to change also the way the recommendation will, the way you will build the engine. You probably will not be able to build such a sophisticated approach because of these requirements. In usability, ease of use of the system by users. In usability, it's another good reminder. If you deal with people who are not very savvy in terms of machine learning, in terms of like technology, they're not technology savvy, you will need to simplify a lot the output that you will deliver to customers. So this is also quality. If you have a system, you return information that is really difficult to digest, and at the end of the day, the people who are supposed to use a system don't use it because they don't understand, you failed. Security, this is classic, but this is also something you need to think about, and this is tough because as an AI practitioner, we don't talk a lot about security, but if you build a credit scoring, if you build this type of score, think about the fact that you might be prone to hacking and security breach. So you want to avoid this from happening, and you will probably need to work with IT security and with other people, but this is something that needs to be thought of. And finally, in terms of audit, so you need to provide auditing tools to the users, and this can be very tricky for users, because how can you give away the explanation? So when you talk about transparency and explainability, this falls into this bucket because I'd say in usability and in the auditing bucket. So if I come back to the credit scoring, for instance, if you have a credit score, so how do you make sure that that when you provide a score, if the end user is not, I don't know, they don't trust that the score is right, or if you made a mistake, or just for monitoring purpose, you want to see what triggered the score. So this also adds complexity to the project, and this is often non-questionable, like especially for a credit score, like in the healthcare system, insurance, banking. The auditing bucket is really, really important, and sometimes a lot of projects will not go forward except if you're able to audit properly the system. Okay, so here, for the purpose of today, because if we had the full day, we could talk about all of these characteristics, but let's focus just on like functional specifications. This is usually what we'll be seeing the most as a data scientist. And for the rest, what I suggest to people is usually make sure you're working as a team, you're working with software developers. You don't have to do all of this. You don't need to be like an expert in security, usability, system efficiency, but make sure the team is, and everybody's able to contribute to this. And usually for AI practitioner and data scientists, we'll focus on functional specification. So here, it's not it. It's not just, oh, okay, so I met the specification, I met the requirements. My model is kick-ass, like it's super good. So I'm done. This is again more complicated than that. So what does it mean to have like a good functional quality? First, you return correct results. This is classic. It needs to work in short, medium, and long term. So you need to be able to adapt the solution. So the solution needs to adapt itself in time. So here, what it means, I'm not talking necessarily about like the most complex reinforcement learning technology just to meet these adaptability requirements. But what I mean is you need to make sure you have the process, can be through active learning, could be just through, a regular, like a monthly retraining, redeployment of the solution, like could be sufficient, and monitoring. So we'll talk about it a little bit later, but this is something that needs to be thought of before, because if it doesn't adapt itself, it's going to be a very expensive solution for a very short amount of time, because at some point you'll it won't be as performant as it currently is. It needs to maintain its functionality in all circumstances. So here we'll talk about robustness, and we'll go outside what a model is. And this is okay. We'll talk about different circumstances that are truly under outside our control. And how do you make sure that your system still works? And finally, risk management. So you need to make sure that you don't cause risk for the end users or for the or for your customer. So those are different things, and there are other characteristics, other things that you need to think about, but these are the most important one in my mind. So here I'll go a little bit through these 4 different topics, and I'll give away a little bit my 2 cents, my tools that I use, my processes. So here, when you talk about correctness, there are 2 different ways you can look at it, and from experience, this is really important to look at these 2 different ways. So here you have on one portion. So we talk about global validation. The global validation is a classic one. It's like your accuracy, your RUP curve. It's about your average error. Like it's one metric. So sometimes when someone says, you know what, my model is super good, it's 89% accurate. So this is global. This is useful because usually, technically, we are going to optimize using this function. Like, okay, I'll try to maximize my accuracy or my AUC or my MAE. But first of all, even if your model is like 92% good, so what reside in these 8 remaining percents? Is it critical or not to the end users? So first of all, this is something, especially when it's a very, very big model, a lot can be hidden in like a global metric. And also from an adoption standpoint. So you want to make sure that the end user, who is not necessarily tech savvy, so you're speaking his or her language. So you want to make sure that you're able to look at specific cases. And here I call it the local validation. So here you build test cases. We'll talk about user acceptance tests in a minute. You'll do some simulations. So you want to demonstrate by using real use case that your model is good and you're able to meet like the most important prediction that you need to deliver. We'll talk about it in 2 slides. So if we look at metrics here, it's just like there are so many metrics. I'm not here to tell which metrics to use. The answer is it really depends, but it needs to be like you really need to think about it. What is the right metric to use? The way you do it usually is that you're going to think about like the business objective. The business objective is usually in business terms, and you need to do the exercise of trying to reverse engineer and saying, okay, to be able to meet my business objectives, I'll need to use this metric to make it happen. Okay. So by doing this, you will make sure that you use the right metric or not. And this is not always easy. There are also some some technical component that you need to think about. Like, for instance, I'll give you an example for a forecasting problem. Depending if let's say, for instance, you try to forecast the demand for something, you might use the average error. So like, okay, on average, I predict I have an error of 10 units every time I predict. So every day, for instance, I'm within 10 units errors. So it might be small or it might be big depending on the use case. But if you're predicting something that is very, very big volume, like for instance, you're trying to predict at Walmart the biggest product, usually what you look at the percentage error. So it's very similar, but it's different because you'll communicate, like for instance, okay, I'm predicting. So I'm predicting with an error of 5%. And when you use this, what's great is usually like Walmart will use percentage in its current process. So you really talk the same language. So this is a way you can do it. And then it's a MAPE that you're using in this case. So it's important to be able to talk the business people, like the PO's language this way. So now now that we talk about the metric here, it's just a simple reminder that the metric, I think I have to do it. I know this is really basic, but just like you cannot talk quality without talking about like the right methodology with validation and test data set. This is just like typical. You will never, please do not talk to end users using the training metric results. Okay, this is usually I see this error quite often. This is basically what you want to avoid. So what you want to make sure is you train, you test different approach using a training data set. And then what we do usually, we'll keep a portion of the data set for training, and then the rest, maybe like the additional 20% of the data set, you use it for validation. And then at the end, and this is often forgotten, but I suggest to use to create this additional data set, a test data set. Okay, so with the training data set, you test different approach. You don't use these validation and test data set for the training phase. But then what you do, you will validate. So every approach that you will test, you will validate against a validation data set. And when you found the best model, you will then use the test data set. And the test data set, so what I suggest and what we will look at, it's not just like the same test that you do with the same metric, but then you do a framework. You're testing a lot of different approach. Everything that we'll talk today, do it on a test data set. This is important. This is not polluted by your trial and errors that you have done with your testing of different approach. And sometimes you do like a grid search, for instance, so you can test thousands of approach with a training and validation data set. So this is not good anymore to be able to validate if it works or not, if it truly works or not. So this is why everything you should do it in a test data set. And I understand you can use like you can use like k-fold cross validation, for instance. This is okay. I won't go in the specific details, but this is something that you need to keep in mind. So everything you do, please do it as much as you can on a test data set that has not been used in the training and the validation phase. Something else that you will want to do is you will also want to test different approach. If I tell you that my model is 81% accurate, it doesn't tell me very much, except if I try different approach. So here, a simple ones would be like a naive approach, a simple approach, and complex. Here, a naive approach, usually there are some good ways you can do it with, for instance, with like if you're using lift. So if you're calculating the lift of a classification, for instance. So this is compared to the normal state. So this is a way a naive approach would work. For forecasting, you can use the maze. The maze, it's essentially looking at the past occurrence, so the -1 occurrence, and if you keep the same, so if you're just late one observation in the past, so how much better are you? So this is just a very simple way. There are some dummy approach that you can use, like a dummy classifier and a dummy regressor that you can use. This is useful. So you can start with this and you say, okay, what's my most naive approach? What performance do I get? And then you should try also a simple approach. So we do that all the time at MoovAI. The worst that you can do is you jump into complexity right away. A good example is the M5 competition. I don't know if you know the M5 competition. It's a competition on Kaggle. So it's essentially the Walmart data set. And it's the ability to predict with accuracy the demand. And a lot of people, they tried like a lot of deep learning approach and beats, like a lot of different approach. But you know what? Most of these approach are beaten by a simple exponential smoothing approach. So if you have not tested the exponential smoothing, it's really basic. So if you don't test this, you might think you have a great solution, but you know, a complex approach, it's not just complex because of the number of parameters. It usually is also complex because of like the pre-processing that you do, the number of the number of signals, the number of features that you're using, and also the way you need to deploy a solution. Sometimes a simple solution, it doesn't even have to be a machine learning approach. It can be rule-based. So it's very basic. It's like a bunch of if else that you can do in an SQL table. So you need to think about simple approach before you jump into complex. And by being able to compare the approach, then you know that you have a winner or not. So here you see, for instance, a way where your performance is going to increase. But sometimes here it can decrease. You can be prone to overfitting, for instance, with complex approach. With simple approach, it's very hard to overfit. It happens, but it's more difficult to overfit. Usually you will tend to underfit and be like to be missing a little bit of performance, but you never know, you know, like it's the no free lunch theorem at the end of the day. It really depends on the data set that you have and the type of problem you're trying to resolve. Here, a very simple ways that you can calculate. So you calculate your errors for your model. For instance, at the left, what you have is like, for instance, the lift and the maze, they will always work this way. The error of your model divided by the error of a naive model. It's easy, but like if it's under 1%, if it's under 1, it means that it's better. So your model has a better error, a smaller error than the naive model. It can also be the opposite. You can look also at like it doesn't have to be a calculation of the error. It can be also the accuracy percentage. But it's the exact same mechanism. So it's a very simple division, but you're able to see if my approach is better than a naive approach. And then at the left, it's exactly the same thing. But what you will do, you will look at the marginal gain of a new model, of a potentially more complex model against a previous model. So you'll be able to do the same exercise and see if you're gaining something to use a new approach. So now I'll go out of, so I'll stop talking about the this global approach, and we'll talk about the local approach. We'll talk about UAT, for instance. So UAT, what it is, it's user acceptance testing. It's pretty classic. It's a bunch of tests that you will do, and if you pass these tests, the user will validate that you pass the test, and if you pass the test, then your solution is accepted, so it can go in production. It's used very often in a software solution, but it's very rare that we hear that for AI solution. We work with Metro, so the grocery stores, the chain, so we did the demand forecasting for like hundreds of store and thousands of products. So it's hard when the business people, they start just looking around thousands of different products. Like they were overwhelmed by the number of predictions they wanted to validate. So what we decided to do quickly is you identify the most important product that you want to validate. And these, you say, if you pass these tests, then the solution is good enough. So here, an example, and sorry, it's in French, but the example would be, for instance, you have 20 different test cases. So these test cases could be 20 different articles, like the top article, or like every article that are in promotion, because promotion is very tricky to predict. So the article, like the promotion that were very, very hard to predict, might be the test that you want to undertake. And if you're able to pass these tests, it means that you're okay to go in production. And here, for instance, you can see it started with 5 tests that were passing, and the rest they were not passing. So you work on on your model. You try to enhance your model until the point where you are passing the 20 tests. Okay. Here, just a small comment. Please make sure that you don't work on the specific test case. The worst would be to say, okay, I have 20 different articles, so I'll try to only enhance these 20 articles. So you need to work on the full solution when you don't pass, because otherwise you will cause some overfitting. So, and you want to avoid this. Okay. Here it could be another example, because these tests can be they will be very granular. So for instance, you want to have like an MAE for syringes. You want to have and those are all different values, but those are values that will be found by the end users. So you just list all of the different tests that you need to do and the threshold. And then as long as you are able to meet the threshold that you set, you pass the test. Good. So we'll talk about adaptability. So now we talked about correctness. I think it was the longest, the biggest section, because like it's very important to us. But adaptability is another dimension of your model. So here we need to avoid a model from degrading. A model will always degrade. It's normal because the data changes in time. Okay, with COVID, we all see it. We all saw it. So a lot of project. So I had a lot of project in production, and then when COVID came up, I was super stressed because like the data structures for my features, but also the different concept, they were all changes. So we call it data drift. So when the data drifts and the data is not the same anymore, your model will degrade. So it will, and you can see here, this is a comparison between the AUC when there's no degradation. So you see here every day, you can see, or I think it's every week. So you see, you will stay in the same range. So it will, sometimes it's good, sometimes it's a little bit less good, but it will stay in the same range. But what you will see when the model degrades is that your performance will drop and your confidence interval will get bigger. So this is something you want to avoid. And here, how you want to avoid is by being able to create your feedback loop. Sometimes it can be automated, sometimes it can be manual. Doesn't really care, as long as you have one and you're able to act quickly. So first you need to monitor the correctness of your model. Then when you find an issue, you need to assess it to bring corrective action. Sometimes it can be just you retrain. Sometimes it can be a little bit more sophisticated than that. You can have to add new data, change the data to make it better, and then you deploy you deploy and integrate the solution again in the platform. So that need to be put in place, because otherwise you have a solution that will not work for a very long amount of time. So here we'll now talk about robustness. Robustness, it's much more than just the model. So now we talk about a model that is very good, hopefully, fingers crossed, and is adaptable in time. So adapt itself in time. But what's happening to your model when you receive different situations? So here, like what's robustness? It's like when you have some observation, so you receive your input. So your input can be like patient record, it can be anything, like it's the data from that you're trying to infer. So you're using so you're receiving an observations, then it goes through your AI system. So you have your system, then it goes into your pipeline, and then it generates results and output. So it could be like a strategy, it could be a prediction, like a plain prediction. So high level, that's it. But then robustness, it's being able to deal with any type of observation you receive. So usually we'll focus on typical context. So this is my data set, and then everything that's outside my data set is considered noise. Sometimes you even remove some noisy observation, and this is okay, because you might not want to train on noise. So you remove it, so it then becomes your typical context. But then you will receive data errors. What's happening if the system generating the data is failing? It can happen from time to time. Sometimes we even add like a weather API, and at some point it switched from the degrees Celsius to degrees Fahrenheit. Like one day it just switched. So this is a data error. How do you make sure that even despite errors, you're able to return results that are okay? Anomalies, black swan event. So when COVID happened, would it return results that are very risky or not? And security attacks. So here, what I'm saying is not we need to do something that's perfect. We need to go back to software engineering. So how do they do it in software engineering? Sometimes it happens that sometimes something weird happens. It's being able to deal with this. It's being able to generalize correctly. So here, so what's happening when there's an extreme case? So what you should do is you should have the capability to observe what you get or the results from your model and say, okay, is this within the boundaries? Is it normal? Should I return this prediction to my end user? If the answer is yes, then you return the AI model output. But otherwise, you don't have to return crappy prediction. You can return like heuristics, or you can return an alert. It's okay to say, you know what, something wrong just happened. You need to go back, because it's better to receive an alert than to receive a prediction that's not appropriate. Okay. And then we'll finish today by talking about risk management. Risk management is very, very broad, so I won't spend too much time on it, and then we'll fall into the question. We'll talk about the, you'll have the opportunity to ask a question afterwards. So risk management is something that that need to happen. Okay, this is something that usually this is where it gets ugly. This is where you see if you will have problems down the road, and we need to be able to mitigate the risk that you identify. So here I'll show you some risk that we're usually looking with customers. So the main risk, data biases. So biases, just general, like the noisy data, poor data quality, missing data, too little database, not enough features, predictive features, for instance. So these are biases that you need to take into consideration. Earlier, when I said, the typical situation or the typical context, it's all about the data that you have. So if your data is very narrow, so you're only predicting a portion of your data set. A good example would be like we're currently working in aerospace. Okay, in the aerospace industry, when you have an economic downfall, usually the airplanes will fly less than when the economy is booming. So if you're only training on the COVID period, where the economy was very, very ugly, and planes were all parked, you will not be able to infer correctly for the period after COVID, where the plane start to fly again. So you need to take that into consideration, and you need to adapt your solution in order to compensate at some point. The correctness of your solution, so we talked about it, when it's very, very complex, tend to overfit. So if there are risks because you have a complex solution, or it's a very complex problem to tackle, you can break it down, or you can spend more time trying to validate. So at some point, if it's very complex, the problematic, you will want to spend more time validating your results, because it will be more tricky. A little bit like what I explained for Metro grocery store, for instance. So we had to be more careful reviewing the performance of the model. The implementation and the security. Implementation can be very painful as well. So the recommendation engine, for instance, that I talked about. So this will be more painful. So spend more time understanding the requirements, the service, we call it SLA. So if it needs to be under 1 second, you need to take this into consideration and measure it very often. Trustworthiness. So the user acceptance test that we talked about. So if you might have problem because your end users might be having trust issues with your model, user acceptance test is a perfect tool to be able to bring them in the bandwagon and to make sure that they really understand that the model is returning appropriate prediction. So they will be also comforted to be able to measure themselves if the model is working or not. So so this is one tool, but there are also a lot of different tools, and it's a little bit the same thing with societal risks. So making sure that so if you're generating risk for the public, like in healthcare, in finance, insurance, so this will also generate a lot of different validation method, additional method, or you'll need to spend more time working on validation of your model. Okay, and I'll leave you on this. I said it before, but this is true. What gets measured gets done. If you only measure accuracy, the accuracy score, so you will have a model that will potentially have a good accuracy score, but against what? This is like, if you don't measure elsewhere, if you don't take this time, so you will have an imperfect model, an imperfect solution, and probably that you will fall within the 85% of the system that will generate erroneous prediction. Good, so that's it. I was wondering if you had any question.
Thank you so much, Olivier. I have a lot of questions for you, but maybe first I'll leave it to the audience to ask their questions. If you have any questions, feel free to just raise your virtual hand and I can call on you to ask your questions. I'll give you a minute before I start asking away. So, okay, maybe I'll start off. Olivier, I have a question for you about application of a model and how you get user buy-in, more or less. So you did explain that there's this trade-off between complexity and accuracy. Totally makes sense, of course. And you know, sometimes whenever you talk to users, they seem to be so focused on accuracy and they sometimes miss the point about complexity. And I wanted to get your thoughts or experience on that, on how do you actually explain this or get user buy-in and explain to them that it's not all about accuracy. And maybe a related quick question as well is, in some cases, you might not have enough data or representative data for a certain category or model. So how do you get users to adopt your solutions as well? Do you just have a general model that you try to tell them, you know, this is a best, you know, this is a best effort type of model? Or how do you deal with such cases where you don't actually have enough data for a specific solution or class?
Okay, so in terms of model selection, I'll take a slide that we had just to, let's think of it.
Yeah.
So here, like the different approach, for instance, so at MoovAI, we always do the three steps. So we're starting with naive, simple, and complex. And usually, like, first thing first, usually the customer, they rarely even have like a naive model or like a rule-based approach. Sometimes you will have, and this is even better when it happens, sometimes you will have some customers, they want to switch because they currently have like a model that's imperfect and they want to gain performance. So this is great because you have like a real benchmark. So here, if they want to, in this case where they want to gain performance, it's okay because they have the benchmark. You say, okay, I'll try to be 5% better than this. And then you never promise anything. You say, okay, we'll try to be better than the approach. And then you do some testing. And so here, let's say, for instance, you're the sample, but you say, okay, I'll do, I don't know, LGBM, and maybe I'll try an RNN. So you can do some, and then you say, okay, we'll try 3 different approach and we'll see what it gives us. And if you're able to meet this requirement, so 5% better than the current approach, then you can stop. So this is how we usually work. We even try to get away from like, okay, we'll try this model, and like they don't even need, at the end of the day, they don't really need to know if it's deep learning or not. It's often just for their own curiosity. We always end up telling them what's the algorithm under the hood, but this is just for curiosity and not necessarily for useful discussion. So that's one thing. When they don't have models, so what we do is we're trying to understand what's the benefit that we're trying to achieve, and then we do the math. We say, okay, to achieve this, we think that you'll need to have that level of performance. It's important to challenge. So at the end of the day, and I don't want to be lazy or something, but usually we tend to see very aggressive benefit. They think that it's going to be it's going to be a revolution. It's rarely a revolution that you're delivering. Like if it's a revolution, it means that the business has very poor like predictive capability. So what you do, you're trying to stay realistic, and you're trying to say, you know what, we'll do it by phase. Let's start. What's the minimum? Like, where are you starting to generate benefits? And then we'll try to get way better than this. But what's the bare minimum where you start seeing benefit? And this is the threshold that you're using, not the ideal state, because then you fall into like the very complex area, and you can spin your wheels for years trying to meet this demand. This is not where you will generate the benefit.
Okay. Thank you, Olivier. Maybe I'll call on Armstrong. Armstrong seems to have a question. So Armstrong, you can unmute, ask your question if you'd like.
Okay, thank you so much, Emma. Thank you, Olivier. What a great talk. I have a question concerning data, because from your presentation, I learned a lot, and it also raises this concern. Given that data is what we have, it's what the world knows, and it changes every time. The model, from what I'm learning, doesn't have control over that. For example, the case of COVID that you gave. What measure is AI like taking to make sure that the life-changing situations, we don't know what will happen tomorrow, and we keep on building models? What kind of changes is AI making to adapt with this kind of uncertainties? I don't know if we will say the entropy of those kind of stable systems. Thanks.
I think this is a good question. This is another slide that I have not shown. So when we talk about generalization, so you have two forces that fight one against the other. So you have the generalization of your model. So the generalization of the model, first, it's a lot of syllables, so I have trouble saying it. But this is key. This is the ability of your model to be inferring a logical results, even though it has not seen the data point itself. Okay, like at the left, for instance, here, if we're looking like at the left, you see something that's not very generalizable. So here, it's only if your new data point is in proximity to the data point that you've seen that the model is going to be good, because this is the only thing it's good at. So your model is not, it's not very good here. It's something we call overfitting, or even if it's not overfitting on paper, but it will be prone to degradation very quickly. So you have, on one hand, because it's not generalizable, it will be prone to degradation. And here it's going to be a pain in the butt, because you will always have problem, and you'll retrain it, and it might not solve the problem. Okay. On the other hand, here at the right, it's a much more generalizable model. So you see here the space where it's good at, it's a lot broader. So here, what it means that it will probably degrade less quickly, and you still need to monitor it, because, for instance, what happened with COVID, or what happened, like, I don't know, in like a lot of different things can happen. So you always need to monitor it. And the worst thing that I've seen, it's usually internally. It's like the IT tool that you have is breaking, and then it generates, like, I don't know, a null value, and it breaks everything. So, but here it will be more generalizable, and your model would be more resilient to changes. So that's first thing, is make sure that you build a generalizable model. And how you can validate that is by making sure you have like a good, the bigger and the more diverse is your data set, the bigger it should be to generalize well. Also, something else you can do that I've seen in real life is a lot of different tests. Like for instance, you generate noise in your data, and this way you're able to build a data set that's much bigger with noisy data points, and you see if you're able to predict good. Sorry, you don't train on this noise, but you're able to validate if you put 50% of noise in your data set and you're still able to predict well, it probably means that you have a generalizable model that will be resilient to data drift. So, but at the end of the day, when COVID happened, but COVID it's extreme. But so what's currently happening day to day, it should not affects very badly your model, but if it does, monitor it and retrain it and make sure that you have the right process in place so that it can adapt itself when it degrades.
Thank you, Olivier. Gustavo.
Hello, Olivier. Thanks for the great talk.
Thank you.
I would like to ask you, what was the hardest challenge that you had to overcome in a machine learning delivery project, and how did you do it?
The biggest challenge, it's always adoption, always. There's a very painful process, that's managing the hype at the beginning, and a little bit a little bit like the question before about the expectation from customers. They have very high expectation at the beginning, and then it erodes because they start seeing they start seeing that it's not perfect. It fails sometime. Also, it's the lack of control. It's very hard for a non-technical person to control the delivery of the system. The fact that you're able to meet certain results, that you're able to predict something, and it's not like a rule-based engine where you say, oh, you know what, you have not met this, I don't know, you're not able to predict this situation, but let's just create this rule and that's it. This is resolved. It's more complex, it's more nuanced, the way you're able to fix a model. So usually this is where it gets very difficult. The adoption is eroding in time, unless you work very hard to keep adoption. So the way you will do it is you try to be aligned as much as possible with the end user. You're not starting off with unrealistic performance. So it's always better to say, okay, what's the minimum, and then we'll try to be better than the opposite. It's also another big problem that I've seen is usually you're trying to have one big model. This is classic. You have one big model, you're trying to resolve everything with your model. You say your model is your system, but it is better when you have several different models. You can have a complex model for complex prediction, and a simpler model for less complex observation. With Metro, for instance, what we decided to do is essentially you're simply using exponential smoothing, for instance, for the skew that are not in promotion, and then we're using LGBM for product that are in promotion, and that is what yielded the best results. It's also the most stable solution. The worst is when you have when it flickers, and sometimes it's very good, but other times it's super bad. That doesn't help with the adoption, and this is often the case. Sometimes it will be very bad when you have only one model. If there's noise in your series, if there's noise for one product, one store, it will be very bad. At least a less complex machine learning model or algorithm will be more stable than a very complex algorithm.
Very interesting. Thank you very much. I think we see, or at least I have seen very little discussion about adoption in the software engineering kind of literature around machine learning. So that's very interesting. Thank you.
Thank you, Gustavo. And again, thank you very much, Olivier. I see we're 2 minutes over the time. Really appreciate you talking to us. And I think, given how great this talk is, I'm sure we'll try to lure you in next time as well. So,
perfect.
On behalf of everyone, thank you very, very much. Really appreciate it. And thanks everyone for attending. And have a good afternoon, I guess.
Great. Thank you, everybody. And thank you for having me. Have a good afternoon.
Thank you.
Olivier. Thank you very much, Olivier. That was great.
Thank you. Bye-bye.
Bye-bye.